AOPS number theory 5.35. M and N are positive divisors such that the GCD of M and N has 5 divisors and the LCM of M and N has 30 divisors. What is the greatest possible number of prime divisors that N could have? So since the GCD has 5 divisors and 5 is prime, that means the prime factorization of it must have p to the power of 4 in it, since that's the only thing that would work to make it 5 divisors, because it's a prime number. So n, since that's the GCD, that means either m or n has to be p to the power of 4, where p is prime. So let's say that n is p to the power of 4. Well, since the LCM of them has 30 divisors, then n could be p to the power of 4 times q to the power of 2 times r to the power of 1, because if you add the exponents together, if you plus 1 and multiply them, it will be 5 times 3 times 2, which is 30, and that's the only way that would make it 30. So the greatest possible number of prime divisors that n could have is 3, p, q, and r, so that's 3. AOPS number 5.36. How many positive integers have exactly 3 proper divisors, each of which is less than 50? Since there are 3 proper divisors, that means it's proper divisors, that means it's a total of 4 divisors, because proper divisors don't include itself. So it must be p to the power of 3, or p to the power of 1 times q to the power of 1, because it's the exponent plus 1 multiply up to 4. So if it's p to the power of 3, 2 to the power of 3 is 8, which would work because it's p squared is less than 50, and 3 to the power of 3 is 27. It would also work. 5 to the power of 3 is 125, and it would also work. 7 to the power of 3 is 343, which would also work. And 11 to the power of 3 is 1331, which won't work because p squared is more than 50. Now p to the power of 1 times q to the power of 1, so it could just be any primes less than 50. So these are all the primes less than 50. There are 15. So the number of distinct pairs, the 15 times 14 divided by 2, if you do this, which is 105 distinct pairs. So 4 over here plus 105 over here is 109 in total.